I am an educator at Unacademy Learning Platform, and there I have started making videos which are totally dedicated for CSIR net preparation. So if you are preparing for the exam, I'll recommend you to watch my videos over there. I'll be solving previous year questions, I'll be giving you tips and tricks and many more interesting stuffs which you will get over there. So all you have to do is install this Unacademy Learning app, and you have to search for my name, that is Nurul Huda, in the search bar. Alright, and you can also click on the link given in the description. From there you can directly go to my profile. All right, and for now let's continue with our topic.
Hey guys, hello everyone. So this video is going to be about inner sphere electron transfer mechanism. So I have already posted my video on outer sphere electron transfer mechanism, and also on your labile and inert complexes. So if you haven't watched those videos, I will recommend you to watch those videos first. Then you will understand this inner sphere electron transfer mechanism more easily. Alright, so in this video I'll be discussing about what is inner sphere electron transfer mechanism. I'll be taking few examples also to explain you in more detail. Then I'll be solving few questions at the end of the video. So I got to know from your comments that you people like that I solve questions at the end of the video. So I will be solving few questions at the end of this video. Alright, so let's start with the topic. So what is your inner sphere electron transfer mechanism? In outer sphere electron transfer mechanism we have studied a lot of things, and we have came to know that in what conditions outer sphere electron transfer mechanism takes place. So about inner sphere electron transfer mechanism, so these are few points which are important for inner sphere electron transfer mechanism to take place. And I'll also discuss along with this that how you can differentiate between outer sphere and inner sphere. So the first point is that the complex should be labile, like one of the complex should be labile and other should be inert. Whereas in the outer sphere electron transfer mechanism, we have studied that both of the complexes should be inert. But here what is there, that one should be labile. All right, so one of the complex should be labile. If the complex is not labile, then there should be like unsaturated coordination number. All right, so these two things are important. Either it should be labile or it should have unsaturated coordination number. That means if it is capable of making 6 bonds or 6 ligand, if it is capable of joining with 6 ligands, it should join with 5 or 4. So then it is called unsaturated coordination number, and it should be labile. For labile and inert, what are these things? You can watch the video. Here is the link for that. So for labile and inert complexes, you can watch this video, then you will understand more well that how labile and inert we are using over here. Now the next point says that at least one bridging ligand is compulsory. So in order to find out that like the mechanism is inner sphere or outer sphere, it can be easily differentiated by seeing a bridging ligand. So if you see any bridging ligand in the complex, and if the ligand transfer is taking place, that is the next point. But if you see any bridging ligand, then you can think that all right, inner sphere mechanism is possible over there. Now the third point signifies that it tells that ligand transfer may happen, but if ligand transfer happens, then it is damn sure you should be 100% sure that inner sphere mechanism is taking place. All right, so this is the best indication of inner sphere mechanism. So if the question comes that you have to find out which of the following mechanism is there, and if you see that from one complex to other complex the ligand transfer is taking place, then you can blindly tick on this inner sphere mechanism. All right, so but this ligand transfer is not it doesn't takes always. If ligand transfer takes place, then it is 100% that inner sphere mechanism is there. But it could be that inner sphere electron transfer mechanism is taking place, yet ligand transfer does not take place. I will tell you with the examples as well, so just wait for that. I will give you with examples. All right, so the next point says that the inner sphere electron transfer mechanism are faster than similar outer sphere electron transfer mechanism. So if sometimes they ask you, if somebody asks you, if somewhere you see this question that which of the rate is faster, inner sphere electron transfer mechanism or outer sphere electron transfer mechanism, then you can say that the inner sphere is more faster than outer sphere. Now what is this, how, why these are named as inner sphere and outer sphere? A sphere is nothing but this bracket. All right, so let's say we have some metal and ligand complex over here, and we have one more metal and ligand complex like this. Now if the electron transfer is taking place from here to here, one sphere to other sphere, this is called outer sphere electron transfer mechanism. But if the electron transfer, like when the electron transfer is taking place from one to other, if it is happening like this, see, if this ml6 and this m dash l dash 6, these are reacting and they form a complex somewhat like this, that m, let's say ml5, okay, and one l forms a ligand with the other, okay, somewhat like this. If something like this happens, then what will happen, ligand electron transfer will now happen from this metal to this metal inside this sphere. So that's why it is called inner sphere electron transfer mechanism. While in the previous case where we have studied outer sphere, we have seen that they come closer to each other. In outer sphere they were coming closer to each other, but they were not getting merged into a single sphere. They were coming closer, and and then the elongation and compression was taking place, like the bond length were changing because of that Frank Condon rule. But here, like, they were not getting like connected or getting into a single sphere. But here what will happen, the two metal like the two complexes, when the electron transfer will take place, when they will come inside a single sphere, and this will happen due to this bridging ligand. So the presence of bridging ligand is very important in order to perform a inner sphere electron transfer mechanism. Now which ligands are bridging ligands? So I have written few ligands over here. These generally are your bridging ligands, like your OH minus is there, then O2 minus is there, NH2 minus, then N3 minus, your carbonyl halide like chloride, hydride, cyanide, then your bromide, iodide, and thiol. So these are some of the example of bridging ligands. So if you see all these, any of these ligand, and few ligands which are not bridging ligands, this is like H2 is not your bridging ligand. All right, so if you see somewhere H2O, don't think it as a bridging ligand. That is not a bridging ligand. Okay, so if you see somewhere bridging ligand, then this inner sphere mechanism can take place. So let's try to understand it more well. First, just revise it once again, just a quick review. The first thing is that one of the complex should be labile and other should be inert. Why one labile and other inert? Because if both of them will be inert, then they will not form a complex. All right, I will explain all of these things. Now one of these one should be, at least one should be your bridging ligand. So one bridging ligand is compulsory over here. Then ligand transfer can happen and cannot also happen. And like the fourth point, inner sphere is faster than the outer sphere. So let's try to understand with an example over here. Okay, so we have example here. So this was the first example, like this was the first reaction which was observed to be like your inner sphere electron transfer mechanism. So I am taking this one only. So we have this complex of cobalt here, and this is a complex of chromium. So this is cobalt NH3 whole 5 Cl, and this is chromium H2O whole 6. All right, so here we have one bridging ligand only present, that is your chlorine. So chlorine is your bridging ligand. See, NH2 is a bridging ligand, not NH3. So mind this thing and remember that NH3 is not your bridging ligand. All right, whereas your Cl is your bridging ligand. So now what is happening under aqueous condition? What will happen? This cobalt is like this H2O6 is going to like it is getting attached with cobalt, and this like the Cl is going to is getting transferred to chromium. So you can see that the ligand transfer is taking place over here, and this NH3 is coming out because of hydration. Understand it like hydrolysis, rapid hydrolysis, or rapid hydration we can say. So that we will understand in the next step. But what is happening, this chlorine, the bridging ligand, is changing from one sphere to it is coming to the other sphere. Now we will try to understand it with the help of the mechanism. Okay, so these things confirm that this is your, like, let's check that how to confirm it. So see, this cobalt over here is in +3 state. So cobalt is in your +3 state, and so your +3 state is your D6. All right, D6 and low spin. Why low spin? Because cobalt +3 like in present NH3 behaves as a strong field ligand when cobalt is present as a +3 oxidation state. So that's why this will be d6 low spin complex, and this chromium is in your +2 oxidation state, and this is your d4. So the ligand is a weak field ligand, so that's why it is d4 high spin complex. Now if you draw the electronic configuration, so this will be like this. So Eg orbital is empty and T2G is completely filled, so that's why it is inert complex. Whereas here you can see one electron is there in the Eg orbital, so that's why it is a labile complex. So this is inert and this is labile. So first, the first condition is fulfilled, that one of the complex is inert and other is labile. Now the next thing is that the bridging ligand is also over there. So what is happening in the mechanism? See, here cobalt is like in +3 oxidation state, and here it is in +2. So what will happen? They will just form a sphere, and one water molecule will go out of the reaction, because this chromium is labile, and like this chromium complex was labile, and it can like the ligands can move out of it. So that's why one H2 molecule has gone out of it, so that the chromium maintains its 6 coordination number. So this chlorine over here is present as your bridging ligand, and the coordination number is mentioned here, that cobalt is in +3 and this is in +2 as it was in the question, and overall 4 positive charge will come on the overall sphere, because 2 plus and 2 plus will give you 4 plus over here. Now next what will happen? The charge transfer will take place. Now when the charge transfer takes place, then see what will happen. The charge transfer is taking place inside this sphere only. So what is happening over here? Chromium is giving one electron to cobalt, so that's why cobalt is now changed into +2 oxidation state, whereas chromium is now changed to +3 oxidation state. Rest of the things are same only. Now what will happen after this? After this the bond will break. Now if you check over here, so what will happen? This here the cobalt is in +2, and this is low spin. All right, so this is your this is your d6, sorry, d7 low spin. All right, so this is now your d7 species, and this one now becomes your d3. All right, so d3, and this is your high spin. So now if you draw the electronic configuration of it, so d7 low spin, if you draw it, so what will happen? D7 means 1 2 3 4 5 6 and 7, and over here if you draw, so it will be 1 2 and 3. So if you can see that this is now inert, all right, and it is now labile. So this is labile and this is inert, means both have changed. So now cobalt has become labile, whereas chromium is now inert. So if cobalt is now labile, then it can break the bond over here. It can lose one electron. It can be like, it can come as a unsaturated coordination number. So that's why it came like this, and chlorine went with chromium because this has to be inert complex. So that's why. So like this, the bridging ligand has changed, like it has shifted from this complex to there. All right, and the oxidation number will be like +2 for this and +3 for this. Now what will happen over here? The next step which we saw over there. So for this complex, this is an unsaturated complex, and the water molecule which we left out in the first step, like it was over here, it came out of the reaction. Now what will happen? It will go and it will bind with cobalt to form a very unsaturated complex, which can easily get hydrolysis, which is called your rapid hydrolysis, and it will all the like your ammonium ion will come out and water will replace them. So you will get a cobalt H2O6 2 plus and this. So the actual reaction is ended over here. This is the additional thing which is happening. So what are the things which has happened in this mechanism? If you pay attention, so what has happened? One labile and one inert complex was taken, then a sphere was formed, then the charge transfer took place inside the sphere. Then what happened? Then the lability and inertness interchanged, and then the bond break to form the product. So this is the mechanism of your inner sphere electron transfer mechanism. Alright, so we have discussed example where the ligand transfer was taking place and inner sphere mechanism was also there. Now let's take another example where inner sphere mechanism is there but the ligand transfer will not be there. Alright, so we have this complex. Now if you see the electronic configuration of this, so this is your 5d5 complex, whereas this is your 3d4 complex. I have told you that all the all the 5d complexes, 4d and 5d complexes, they all are low spin. So if you draw d5 low spin, so you will get an inert configuration, whereas this is your d4 high spin. So if you draw a d4 high spin configuration, you will get a labile. So you have a inert and a labile complexes. The electronic the oxidation state over here for iridium is +4, whereas here is +2. In the product, iridium is coming as +3 oxidation state and coming as +3 oxidation state. So the same thing is happening here, and the bridging ligand is chlorine. So how the mechanism will proceed? See, these two things will react and you will get a complex like this. So it will be like iridium chlorine 5. So since it is an inert complex, so it will be like the bond will be like that only. And here you will be having your um, chromium and H2O 5, and one H2O will be present as, like, it will go out of the reaction in the aqueous medium. All right, so this will take place like this because this is labile, so that's why it has happened with this. Now this is in your +4 oxidation state and this is in your +2 oxidation state. Now the electron transfer will take place and now they will convert it into Cl5 iridium +3 and chlorine will be attached till now also, H2O5. All right, so it will also be +3. So now electron transfer has done. So electron transfer has already done. Now what will happen? This, since now iridium +3, that is your d4, and this is also low spin only. So that's why d4 low spin will be your inert only, and this chromium +3 will be your d3, that will also be inert. So both of them has been inert. So that's why no bond can be like the thing which was earlier like that. It should be like that only. So this bond will break like that. So what will happen? It will be like iridium Cl6 and +3, because this is your +3 in your +3 oxidation state, and plus Cr H2O5, till now it will be 5 and +3. Now what will happen? One H2 which you have left over here, it will come and it will join and it will form your CrH2O6. Okay, and 3 plus. So this, like this, the electron, like the reaction should proceed, so that the ligand transfer didn't take place and the electron transfer happened. So this is also example of your inner sphere electron transfer without ligand transfer. Okay, so this was about your inner sphere electron transfer. Now let's take few examples, let's take few questions from previous CSIR exams and let's try to find it out how to solve them. Alright, so this question came in June 2015 for 4 marks. The question says that the water plays different role in different reactions. So you have 4 different reactions and you have 4 different options. I didn't wrote all the options over here because like it was like A1 and A and like that. So we'll just match it out and find it out that what will be the answer. Okay. All right, so the option for the question was like this. So how to approach this type of question? See, in the first option you can see that the calcium is changing into Ca2 plus. That means the oxidation state is 0 over here, whereas here the oxidation state is +2. That means the oxidation is taking place for calcium. Now if the oxidation is taking place for calcium, there must be the other thing which is helping in oxidation. That means that is your oxidizing agent. All right, so oxidizing agent, so this is your oxidizing agent, that is water. Now oxidizing agent is only oxidant, so that means that here in first step it is acting as a oxidant. All right, these all concept I have explained in the video of outer sphere electron transfer mechanism. Now we'll leave the second one, like just leave it there and check out the third one. Here you can see that the oxidation state of magnesium is +2 and here also +2, so nothing is happening, no oxidation, no reduction, so you cannot predict anything here. So let's leave it here as well. All right, so let's move on to the third one. Okay, so here you can see it in the second option also it should be Cl minus. So here also the oxidation state is not changing, so we'll leave it here. In the fourth option you can see that the fluorine oxidation state is 0 over here, where here you have -1 oxidation state. That means the oxidation state has reduced, that means it has done reduction, and that means the other thing, that is the water, is helping in reduction. That means it is reducing agent, and reducing agent is only called reductant. All right, so two things we have find it out, that the first one is oxidant and the second one is reductant. Now if you will see the third option, you will see that magnesium like water is forming complex with it. If it is forming a complex, if it is behaving as a ligand over here, so what ligand do, it donates electron. So what these things are doing, they are like this, um, H2O is doing, it is just donating its electron to magnesium. So in order to, when it is donating the electron, it is behaving like the electron acceptors are base. So that's why these are electron donors over here. Since it is a complex form, so that's why this is a donor over here, and that's why it is behaving as a base in this case. So remember this thing, that electron acceptors are acid and electron donors are base. Now in this step, in the second one, if you'll see, you will think that it is a complex found, but no, complex is never found without a metal. You need a metal over here. Here you have chlorine, so here is no complex found. So that's why the base concept or the electron donor and acceptor, those concept will not come here. So the left out option will be the acid. So here this thing is behaving as acid. All right, so like this the question has to be done for 4 marks. Okay, so we'll take this last question. This question was asked in June 2014 for 4 marks. The question says that consider the following reaction undergoing outer sphere electron transfer mechanism. First reaction is this, that iron is getting changed from +3 to +2. And in the other option also, iron is changing from +3 to +2. The rate of the first reaction is 4 mole per second, and for the second reaction it is 3 into 10 to the power 7 per mole per second. So as compared to this one, so this reaction is so fast, and the unit is telling that the reaction is of second order. So those are the secondary things. So all right, so the question says that the enhanced rate constant for the second reaction is due to. So for second one, why the reaction rate is so high? So that's all what they are asking. So iron is same, only the metal is same, only the ligand is changing. So something is happening because of ligand. So this PHEN is your phenanthroline. All right, so phenanthroline, the first option says that the phenanthroline is a pi acceptor and allows mixing of electron donor and acceptor orbital that enhances the rate of reaction. So this is the first option which tells this, that it is a pi acceptor, and due to this the electron donor and acceptor orbital get mixed or they get overlapped, and this enhances the rate of reaction. The second option says that the phenanthroline is a pi donor ligand and enhances the rate of reaction. So one thing you should know, that phenanthroline is a pi acceptor ligand, not pi donor. So this option cancelled out. So phenanthroline is a pi acceptor ligand. All right, so remember this thing. Now the third option says that phenanthroline forms charge transfer complex with iron and facilitates electron transfer. So this doesn't make any sense. It is saying that phenanthroline forms charge transfer complex. Obviously the outer sphere electron transfer is taking place, so phenanthroline is forming a charge transfer complex. So this doesn't like, it is saying that phenanthroline forms charge transfer complex with iron and facilitated. So this doesn't make any sense. So that's why we can't like totally rely on this option. So let's move on to the other. The other says that the phenanthroline forms labile complex with iron and facilitates electron transfer. So if you'll draw this, if you'll check the electronic configuration of these two, you will find these are not like labile, both are inert. So that's why this option is also not correct. All right, because phenanthroline is not a strong field ligand. So that's why the only option left is your first one, that is phenanthroline is a pi acceptor and ligand, and it allows mixing of electron donor and acceptor orbitals that enhances the rate of reaction. And in simple words, you can say that the phenanthroline is a pi acceptor ligand and it has low lying pi orbitals. That's why they get mixed or they get like overlapped with the acceptor orbitals, donor orbital. So it get overlapped with them, and that's why the reaction rate is enhanced. Means it has low lying electronic orbitals, pi acceptor orbitals, low lying pi orbitals, and they get overlapped easily with the metal orbital. So that's why the rate is enhanced over here. All right, so the option will be option number first. So in this way the question has to be done from your outer sphere and inner sphere electron transfer mechanism. So if you people get any question related to this topic, you are most welcome, you can ask me them, and if I'll be also searching them, and I will include them in the revision classes when I will start making the revision classes before the exam. All right, so for now that's all for this video. I hope you people liked it, and if you like my work, if you like this video, And if you are new to this channel, I request you to subscribe the channel. I will be uploading regular videos and you will get notification for that if you subscribe it, and that also motivates me to make good videos for you guys. So thank you for watching. Thanks a lot.